maybe I can start for now, and those who are still downloading MATLAB can catch up a little bit later. All right. So no matter Xfoil or Mfoil, let's use a NACA 0007 airfoil to get started. So in Xfoil, just type NACA 007 and go to upper and alpha 0, right? In Mfoil, you put like 007 over here, and alpha equal to 0, and click run. You should get the same pressure distribution, right? This plot and this plot should be exactly the same. They are just having different aspect ratios. All right. Okay. So today, the first thing we'll do is to start looking at now a viscous flow. So in MLab, just click the invisit button. If you click it once, it should say viscous now, right? And then you click run again, you should get a viscous solution. In Xfoil, the way you do is you type VISC, viscous. It is going to ask you for a Reynolds number, right? And actually, let's start by having a relatively small Reynolds number 1E5. Okay, here, let's also change it to 1E5. So, and click run. All right. And once you have 1E5, you type alpha 0 again, you should see an updated plot.
How do you get the plot? How do you plot in Xfoil?
In Xfoil, it's just the alpha 0. ALFA space 0. The plot should be updated, yes.
How do you first get it to appear, the plot? In the very beginning. You opened this and had the plot already open.
Oh, that's because I just typed the alpha 0 before you came over here.
Oh, okay.
Yeah. Okay. Right. So the reason I said 10 to the 5 or 100,000 is a low Reynolds number, right? May not be intuitive to you. But just to think about what 10 to the 5 actually means. So it'll be good if you, well, when we get to the quiz for viscous flows, you have to remember the definition of Reynolds number, right? The Reynolds number is density times velocity times certain length. In this case, the length is the chord length, divided by viscosity, right? 4 things come into play here. 3 are in the numerator, 1 in the denominator. What's in the denominator is viscosity, so the higher the viscosity is, the lower the Reynolds number is. And 3 appears on the denominator, density, velocity, and length, right? For these 3 numbers, the higher it is, the higher the Reynolds number it is. Now, hopefully you all know roughly what is the density of air, right? It's on the order of what? Yeah, it's like 1 kilogram per meter cubed, right? That's close to the ground. Then if you go up to like the cruise altitude of airliners, it drops to like 0.3, right? 0.4. Okay, so let's say the density is just 1 kilogram per cubic meters. So anybody knows the viscosity of air? What is mu? So air is really not so viscous. The viscosity is on the, I mean, depends on temperature. But the order is about 10 to the minus 5. Okay, so that's the viscosity of air, 10 to the minus 5. And then because the density is around 1, so no matter if you're talking about dynamic or kinematic viscosity in SI units, it's always about 10 to the minus 5. Now we know these 2 numbers, rho and mu. The remaining 2 numbers that determines Reynolds number is the chord length and flow velocity, right? Okay, so if the Reynolds number is 10 to the 5, and if the density is 1 and viscosity is 10 to the minus 5, what is the product of velocity and chord length? Again, Reynolds number, which is 10 to the 5, is equal to rho times v times chord length divided by mu, right? And rho is 1, mu is 10 to the minus 5. So what is the product of v and c, chord length? It's about 1, right? So a Reynolds number of 10 to the 5 corresponds to velocity times chord length equal to 1. And so if chord length is 1 meter, then what is my speed. About 1 meter per second, right? Really slow. That's why I'm saying like 10 to the 5 is a low Reynolds number. Or if the chord length is 10 centimeters or 0.1 meter, the flow speed is 10 meters per second, right? So Reynolds number of 10 to the 5 corresponds to like a small model airplane. Okay, and for anything bigger that carries people, the Reynolds number is going to be a lot higher than this. So let's first look at what the boundary layer is going to be like for this low Reynolds number, and then we'll switch to a higher Reynolds number and look at how the boundary layer behaves. Okay, so first of all, let's examine these two plots. These two plots are pressure plots, CP, right? And you're going to see both a black, okay, so in Xfoil, you are going to see a black dashed line and a colored solid line. In M-foil, you're going to see a dotted line and a solid line. So the dotted or dashed line corresponds to the inviscid pressure distribution. Okay, these are the same line if you did not turn on viscosity. So if the whole flow field is inviscid, then the line should be the dotted or dashed line. The solid lines, the solid colored lines, are the pressure distribution taking into account of the boundary layer. Okay, you look at this. Can you tell me that which pressure is higher? Is the inviscid pressure higher or viscous pressure higher? The inviscid pressure is higher, right? Remember, for the CP plot, the higher the plot is, the lower the number is, right? It's reverted. So the dotted lines are lower, means they have a higher pressure. So the effect of the boundary layer, in this case, makes the pressure lower. So why is it the case? So remember in lecture today, we talked about the displacement effect of the boundary layer, right? The effect of the boundary layer to the flow field outside of the boundary layer is acting as if, right, it is the existence of the boundary layer makes the airfoil effectively thicker because the outside streamlines are displaced so that they are further away from the airfoil, right? So the effect of the boundary layer to the outside the streamlines are artificially making the boundary layer thicker than it actually is. So if you think about the effect of a thicker airfoil, right? If you make the airfoil thicker, the pressure is going to become lower, right? Yes?
So is that the effect that the displacement thickness we talked about last day, is that pressure multiplier?
Exactly. The displacement thickness we are talking about today is exactly that, right? Yeah, so the displacement thickness is how much the existence of the boundary layer displaces the streamlines outside of the boundary layer. Yeah, good. Okay, so the effect here is to make the airfoil appear as if it is thicker and therefore has a lower pressure. So it is obvious if you actually make the airfoil thicker, right? So remember the top of this is at negative 0.2 something, and if you make the airfoil 0.009 and click run again, you're going to see that the lowest pressure is going to be even lower, right? So a thicker airfoil means a lower pressure. This can be also reasoned from the conservation of mass, right? So the existence of an airfoil means that the streamlines that are upstream has to be squeezed over in a smaller area, right? Because some of the area that the streamline has to go over is now occupied by the airfoil. So by mass conservation, the same mass has to go through a smaller area, means the flow velocity has to be higher and the pressure has to be lower, right? So basically, a thicker airfoil means lower pressure. So the boundary layer makes the airfoil as if it is even thicker, right? And as a result, makes the pressure even lower. Okay, make sense? All right. Okay, next let's actually change the angle of attack and make it 2 degrees angle of attack, and in this case in Xfoil we just type alpha 2. All right, and now in both cases you should see the colored lines now split into black and blue lines. And these colors are also represented on the airfoil so that it is obvious that the blue line corresponds to the upper side and the red line corresponds to the lower side. Okay, so are you able to get to this point? Have you finished installing?
I have the code of it was pulled up in MATLAB, but how am I supposed to run it?
Oh,
where
go
I
to
have
this
one
one.
thing here?
Okay, sure.
I think the dot is the.
All right, so let's look at the pressure distribution at the 2 degrees angle of attack. Right, so now what is the difference between the inviscid pressure and the viscous pressure? Can you identify the effect of the boundary layer as not just making the airfoil thicker, but also there is another effect, right? Particularly recall thin airfoil theory, right? So you want to say something? Yes, the inviscid has a higher peak, right, than the viscous pressure distribution. Now, if you recall thin airfoil theory, right, a lower peak and in particular a smaller gap, right, between the upper and lower side of the pressure means what? So what does the thin airfoil theory tell you if you see the gap between the pressure distributions become smaller and the peak becomes lower? What does that tell you? Yes, a shallower angle of attack, exactly, right? So that means in this case, the existence of the boundary layer makes the airfoil behave as if it is at a lower angle of attack. But in reality, the angle of attack didn't change, right? It's still 2 degrees. So effectively, it's like the airfoil has pitched down a little bit, or the trailing edge has raised a little bit, right?
Even though it's up.
Yeah, right, right. So even if the flow is going in upwards direction, but if the airfoil has pitched down at the same time, then the angle of attack relative to the flow is not going to be as high as 2 degrees, right?
Okay.
Yes?
Is that like related to magnitude? Like we put like -2 degrees and alpha, it have just opposite magnitude.
Yes, the question is, if we put -2 degrees, would the same thing happen? Would the airfoil behave as if it has a higher or lower angle of attack? We'll first analyze the reason why the existence of the boundary layer make the airfoil as if it is pitched down a little bit, right? Then let's think about your question. Okay, so to answer the question, why does the airfoil look like as if it reduced the angle of attack from 2 degrees to maybe 1 point something degrees? Let's look at the effect of the boundary layer towards the trailing edge, right? In the previous case, we saw that the boundary layer works as if it makes the airfoil thicker. In this case, it is doing the same thing, but not symmetrically anymore, right? Can you see from this plot that which side has a thicker boundary layer? The upper side, right? Yeah, the upper side has a thicker boundary layer, which means that the airfoil behaves as if the displacement effect of the boundary layer, and the displacement effect is more for a thicker boundary layer, right? Remember the displacement thickness. So the upper side is displaced even more than the lower side. That creates an effect similar to raising the trailing edge a little bit upwards, right? So that is as if you're pitching down the airfoil. Okay, so if you put it as a -2 degrees angle of attack and run it, and look at the trailing edge, what's going to happen? The lower side now has a thicker boundary layer, right? So the airfoil is going to behave as if it is at like -1.5 degrees. All right. Okay, so this is the effect of the boundary layer to lift, right? So you're gonna see because of the boundary layer, the slope of the lift is not gonna be as large as it is before, right? So at the same angle of attack, a viscous flow, an airfoil at the lower Reynolds number is gonna have less lift compared to an inviscid flow or higher Reynolds number flow. Okay. All right. Any questions? All right. So now let's go back and to 0 degrees, and I'm gonna walk you through the other plots. So alpha 0, and the other plots you can select from here. So the default is pressure coefficients. That's what we have already been looking at. And the next one is skin friction coefficient. So in Xfoil, what you do is you go to a submenu called the vplot, VPLO, and the 2 dots means you are going to a second level submenu. And to plot the skin friction, you type CF. So that's the skin friction over the airfoil. All right. And this is the same skin friction we went over in class today. So the skin friction is defined as the friction force on the surface per unit area, non-dimensionalized by half of rho u infinity squared, right? So the same kind of non-dimensionalization as the pressure coefficient, because both pressure and friction are expressed in terms of force per unit area, right? Except for the pressure is in the wall normal direction, the friction is in the wall tangential direction. Okay. And in class, we looked at the flat plate and looked at how the skin friction changes as you walk along the x-axis. We saw that as the boundary layer becomes thicker and thicker, the skin friction becomes less and less, right? For the flat plate case, the skin friction goes like 1 over the thickness of the boundary layer. In this case, is it consistent? Right? At the leading edge at x equal to 0, the skin friction is very high. Okay, and as you go towards the trailing edge, the skin friction becomes 0 at the trailing edge. So there is actually 2 effects over here. One is the boundary layer becomes thicker, grows thicker and thicker towards the trailing edge, and also the shape actually changes. We're going to later see the shape. So the compounding effect makes the skin friction decays even more rapidly than 1 over the thickness of the boundary layer. Okay, that's skin friction. So that also tells you viscous flows over boundary layer is going to give you non-zero drag. So actually the drag comes from 2 parts. One is from skin friction, right? The skin friction is in which direction? What is the direction of the skin friction on the airfoil? It's towards the left, right? Towards upstream. Sorry, I said it wrong. The force of the airfoil acting on the fluid points left, but the force of the fluid acting on the airfoil points towards the right. So that's the drag component. Okay, so there is so these points towards the right, except for at the very leading edge, which is a small fraction of the geometry, right? So they point in the drag direction, and the skin friction contributes very little to lift, even at non-zero angle of attack, because the skin friction points tangential to the surface, right? And the area over which the tangential direction has a significant vertical component is very small, okay? Right, very small. Area is very small. And if you look at the skin friction coefficient, it's like 0.0 something. Compare this to the pressure coefficient, which is non-dimensionalized by the same thing, right? The pressure coefficient is point something, right? It's on the order of 1. So there is a scale difference in the force. There is also a scale difference in the direction, right? The pressure points mostly on the up and down direction, while skin friction mostly points on the left and right direction. So the contribution of skin friction to lift is almost nothing. But the skin friction contribution to drag is not almost nothing, right? It's mostly is in this direction. Now, how about the contribution of pressure to drag? Can you look at this plot and identify if pressure actually contributes significantly to drag or not? Or the difference between inviscid and the viscous pressure, does that contribute to drag? The difference is almost nothing near the leading edge, right? But the difference is pretty significant. It's almost like 0.2 at the trailing edge, right? And which direction does this difference act on? Right? Can somebody think about what is the so the viscous flow has a lower pressure near the trailing edge, right? So that means the viscous flow is sucking more at the trailing edge. It's sucking, I mean, think about what is the normal direction at the trailing edge. It's pointed slightly towards behind the airplane, right? So even the pressure, right, the viscous flow causes a pressure difference which contributes also to the drag. Okay, so there are really two sources of drag caused by viscous flows. One is it changes the pressure distribution, and that gives you additional pressure drag. It also gives you additional skin friction, which also contributes to drag. Okay, so neither components are negligible. All right, make sense? Right. For lift, you only need to consider pressure, but for drag, you need to consider both. Okay, next, displacement thickness. That's quantitatively plotted over here. So this is basically saying that when you go towards the trailing edge, the streamlines are displaced. The inviscid streamlines outside the boundary layer is displaced by about 1% of the chord length. Right? Or it's almost like the trailing edge is thickened by about 2% of the chord length. Right? Because on both sides, it has a displacement thickness of 1% of chord length. So if you combine them, the trailing edge is as if it has a 2% thickness of the chord length. In Xfoil, what you do is in the V plot, you type a dt. That actually gives you 3 different boundary layer thicknesses, right? That's actually exactly the 3 different thicknesses we discussed in class. Do you remember like what are the 3 different thicknesses? The thickest one is the so-called 99% thickness. Okay, it is at this location when you are this much away from the wall. The velocity over there is 99% of the velocity outside of the boundary layer. Or when you go beyond this thickness, the difference between the velocity and the velocity outside of the boundary layer is less than 1% of the velocity outside of the boundary layer. All right, so that's the 99% thickness. It's usually the thickest. The second and the third one are the displacement thickness and the momentum thickness. Remember which one is higher, which one is smaller? Yeah, displacement thickness is higher, right? Because in the definition of momentum thickness, the integral is multiplied by another u over u infinity. So the momentum thickness is guaranteed to be smaller. And actually, in this scenario, both definition of displacement and momentum thickness are not using u over u infinity. Instead, they are using u over ue, where ue is the velocity outside of the boundary layer at that local position. right? This is because we want to make sure that the contribution into the integral should be 0 when you're already outside the boundary layer, right? And when you're outside the boundary layer, we have u equal not to u infinity over airfoil, but u equal to the velocity outside of the boundary layer. So we use the velocity outside of the boundary layer as denominator, so that u over ue would be equal to 1, right? So 1 minus u over ue would be equal to 0. So we always guarantee that in the integral, we should have 0 contribution from the flow outside of the boundary layer. Okay, so this is the that means the middle one is the displacement thickness, the lowest one is the momentum thickness, which is also plotted over here. All right. Okay. That's the momentum thickness, and the next one is the shape parameter, or the ratio between the displacement and the momentum thickness. Right? We said that because the displacement thickness is always larger, the ratio is always above 1, right? We see that this ratio goes from 2.2 all the way to about 4. All right. Okay. And in Xfoil, just the type H gets you the shape factor. Okay. And edge velocity is the velocity outside of the boundary layer. So that's the denominator we use when we are integrating the velocity profile for the displacement and the momentum thicknesses. So that's yeah. And finally, something I haven't discussed in class yet, but we'll get to when we start to talk about the transition and turbulence. So this is a model parameter for how unstable the boundary layer has become. So when the instability grows to large enough magnitude, the boundary layer is going to transition into a turbulent boundary layer. The most important thing you are going to learn in 16100, you are going to learn more things if you take later classes, but in here, we're only going to stress 2 points. In a turbulent boundary layer, the skin friction is more. Right, you have more friction in the turbulent boundary layer, but a turbulent boundary layer is less easy to separate. Okay, so the consequence in designing and analyzing airplanes and other things is that if your drag is dominated by flow separation, you want turbulent boundary layers, because turbulent boundary layers doesn't separate as easily. If your drag is dominated by skin friction, you want laminar boundary layers, because laminar boundary layers has less friction. Okay, so that's the only 2 things we are going to stress, not now yet, but later. Okay, and finally, we have RE theta. So that's basically, theta is momentum thickness, right? RE theta is basically momentum thickness times density times u infinity divided by viscosity. That just gives the momentum thickness in a different scale, like a non-dimensional scale. So as opposed to if you just plot momentum thickness, it's on the order of 10 to the minus 3, right? But if you plot the Reynolds number based on theta, you get like several hundred. Okay. And over here, yeah. Anyway, so any questions for now? Yes?
Did you say turbulent boundary layer is easier or harder for flow separation?
Turbulent boundary layer is more resistant to flow separation, so it separates later, right? So if you put some roughness upstream to trip the boundary layer into turbulent boundary layers, it can delay flow separation.
And you want flow separation, or you don't want flow separation?
Most of the time, if you don't want drag, then you don't want flow separation. Yeah. Okay, we'll talk about flow separation next week. Okay, so the last thing I want to show is the effect of Reynolds number. So here we have been always looking at the Reynolds number of 10 to the 5. So let's increase the Reynolds number by 2 orders of magnitude. So that gives us a Reynolds number of 10 to the 7. Okay, if you think about what does 10 to the 7 mean, okay, that means the velocity times chord length is equal to what? again, density is about 1, viscosity is about 10 to the minus 5, right? So Reynolds number is equal to 10 to the 7 means if you have a chord length of 1 meter, that means you're flying at what speed? What? 100 meters per second, exactly, right? So 100 times faster for the same chord length. Or 10 times the chord length, 10 times the speed, right? Or let's say if you have a chord length of 10 meters, it's a very large airplane, or let's say 5 meters, then you're flying at 20 meters per second. All right, so that's kind of the scale. It corresponds to probably some kind of a general aviation airplane. It's somewhere between that and the jetliner. Okay, so that's moderately high Reynolds number. Over here, you can type RE and you enter 1E7, right? So that switches you to a higher Reynolds number, alpha 0. That gives you the pressure distribution. So first of all, we see that the gap between the inviscid and the viscous pressure distribution almost vanishes, right? So that means for a higher Reynolds number, the viscosity is lower, right? Remember today we discussed the ratio, right? The thickness of the boundary layer over the chord length is proportional to square root of 1 over the Reynolds number. So if I increase the Reynolds number by a factor of 100, I expect the boundary layer to be 10 times thinner, right? We're going to see this is not going to be exactly the case because the flow is going to transition to turbulent boundary layer, and the turbulent boundary layer is going to behave differently. So this is not exactly true, but it is true for the front part of the boundary layer before the flow transitions. Actually, on the right plot, you can see this kink here. That kink is actually a pretty good indication that the flow transitions over here. So the front maybe 40-ish% is laminar, and the boundary layer is going to be almost exactly 10 times thinner than in the previous case. The later 60-something% is going to be turbulent, and it behaves differently from the laminar boundary layer. So whatever the case, the boundary layer is much thinner, and as a result, the influence of the boundary layer, the displacement effect of the boundary layer is much less, right? And as a result, the pressure distribution is not as much affected by the existence of the boundary layer. Okay? And similarly, if you put it at an angle of attack of 2 degrees, for example, you're going to see the pressure distribution also doesn't affect being affected that much, right? That's because, again, although the boundary layer is still asymmetric at the trailing edge, but because they are so thin, the effective angle of attack is not much influenced. Okay, let's also look at other plots. Skin friction coefficients. Oh, this is a very clear demo of laminar and turbulent boundary layers, right? First of all, on the laminar boundary layers, you can see that the skin friction coefficient is actually much less than in the previous case. So in the previous case, it's on the order of 10 to the minus 2, and in this case, it's on the order of 10 to the minus 3, almost exactly 10 times smaller, right? That's again the square root type of dependence. But as soon as the flow transitions, the skin friction gets a lot higher. So that's the effect of the turbulent boundary layer. All right. Okay. And displacement thickness. Again, like instead of on the order of 10 to the minus 2, now this is 10 to the minus 3. Okay. And again, you see different behavior after the flow transitions into turbulent boundary layers. Momentum thickness, it's the same thing. Let me actually do it over here, V plot and dt, so that gives me all the 3 plots. So 99% thickness, and in turbulent boundary layer, the 99% thickness is actually a lot higher than the displacement thickness. Let me actually do it at alpha 0 plot and dt, right? So that's for turbulent boundary layers. The momentum the 99% thickness is a lot higher, but the displacement thickness is going to be not that much higher than the momentum thickness. That makes the shape factor, if if you switch the shape factor, the shape factor for turbulent boundary layer is going to be a lot lower than the shape factor for laminar boundary layers, right? So for laminar boundary layers, the displacement thickness is more than twice as thick as momentum thickness, and for turbulent boundary layers, the displacement thickness is only something like less than 40% higher. Okay, and edge velocity, not much to say over here, and amplification. So you're gonna see that here in this model, we are marking the boundary layer to transition after the unsteadiness, after the instability reaches 9, right? And yeah, in Xfoil or Mfoil, you can actually change this critical amplification factor, change this 9 to something else to simulate the effect. For example, in a wind tunnel, you already have some dirty air, not exactly smooth air coming from free stream, and the effect is actually a lower critical amplification factor because initially you have some unsteadiness coming in. All right, and finally, RE theta. So that's another quantity you can look at. So for laminar boundary layers, it stays in the hundreds, right? So like maybe maximum going to about 1000 before you're going to transition to turbulent boundary layer where the RE theta would further grow. All right, okay, so that's our walkthrough of how the boundary layer behaves in a typical airfoil and how it depends on Reynolds number, and in particular, how does the airfoil characteristics, how does the flow around the airfoils, the envisaged flow outside of the boundary layer, react to the existence of boundary layers. So next week we are going to study something complementary, that is how the boundary layer itself is going to react to the change of pressure, to the pressure distributions along the development of the airfoil. So if we understand both, right, if we understand how the existence of the boundary layer is going to change the flow around it, and particularly change the pressure distribution, and we understand how does the pressure distribution changes the behavior of the boundary layer, then we understand completely how viscous flows are going to change the airfoil characteristics, right? Okay, and in particular, how to design airfoils if you want the airfoil to behave in a certain way. Okay, so see you next week.